Hello, I'm Richard Jacob from Matrix Science. This presentation describes how sequence query can be used to find a match to a peptide with an unknown modification, or even when the peptide sequence differs from that in the database. You will remember from the introduction that sequence queries are searches where mass information is combined with amino acid sequence or composition information. The best known example is a sequence tag search, where a few residues of amino acid sequences are interpreted from the MSMS spectrum. This was first published in 1994 by Matthias Mann and Matthias Wilm. You can enter sequence tags and other types of query into the sequence query form. Remember that all the search parameters, including enzyme specificity, modifications, and precursor charge, will apply to this type of search. Mascot will look for a match between the tag and the ion series specified by the instrument type. Note that Mascot will only try to match the tag against ion series formed by a single backbone cleavage and maybe a neutral loss like Y or B asterisk or Y doubly charged. It won't try to match against side chain cleavage fragments like D, V, W, or internal fragments. Unless you have high energy fragmentation and are able to distinguish leucine from isoleucine by side chain cleavage fragments, then this tag is wrong. It should be isoleucine or leucine. Ambiguity in a tag is fine as long as it is recognized and spelt out. Most times, you won't know whether a residue is glutamine or lysine. Phenylalanine is almost identical to oxidized methionine. If the peaks are weak, are you sure you have a mass difference of arginine? Or could it be an amino acid pair, valine and glycine, and the intermediate peak is missing? If the sequence is in the database, it is easier and safer to perform a MSMS search of the peak list. In this sense, the standard sequence tag is obsolete. The error-tolerant tag, which can find a match when there is unsuspected modification or a small difference in the sequence, is very powerful and very useful. Imagine we had an unmodified peptide of MH plus 1314.7 and we interpreted a tag of TISP in the B singly charged ion series between peaks at 614.3 and 911.5 m/z. What happens if there is a modification or single nucleotide polymorphism, a SNP, that increases mass by 100 Daltons? If the mod is on the N-terminal side of the tag, all the masses shift up by 100. However, if it is on the C-terminal side, only the peptide mass changes. If the tag was in the Y ion series, the reverse would be observed. The error-tolerant tag allows for this. In effect, it allows the peptide mass to vary and allow the tag to float. However, the tag must stay attached to one end or the other. Either both fragment ion masses are unchanged, or both fragment ion masses shift by the same amount as the precursor. This causes a huge loss of specificity. So we cannot allow E-tag searches with very wide peptide mass tolerance, greater than 1% or greater than 10 Daltons, or with no enzyme specificity. The enzyme specificity in an E-tag search is never fully specific. In any case, because one end of the peptide can just extend until it finds a cleavage point. Tags can be entered with the high mass fragment on the left or the right. These two tags are identical. Mascot allows multiple tags in a single query. That is, you can call multiple tags from a single MS/MS spectrum. Tags are scored probabilistically. If one tag is wrong, you can still get a good match for the tags that are correct. If one tag in a query is an E tag, then all the tags for that query are treated as E tags. Not all tags in the search, just in that query. Finally, you cannot mix iron qualifiers with tags or E tag qualifiers. It would just be too complicated. A lot of people call tags by inspection, using a calculator or a table of mass values. An alternative is to use Mascot Distiller. Here's how it works. Maximize the window. Choose a likely looking peak, such as 987.384. Right-click to start a tag. Click on any arrow to extend the tag. Where there's a choice, I just go for the biggest peak and stop when it starts to look tricky. Going to the right, there's no choice, and the descender from the second I, which equals isoleucine or leucine, is dotted to indicate we've reached the precursor mass, which is a bit of luck. Going to the left, there is a choice of 3 residues. Zoom in for a closer look. No doubt that tryptophan is the most intense, so we click on the arrowhead to extend it. Again, a choice of 3. We'll go with the isoleucine. Methionine looks a bit dodgy, so we'll go with the isoleucine again. No choice. Good. Lots of choice. Maybe time to give up. Restore the window arrangement. Here's our tag, but is it correct? Well, we just happen to have database search results from this spectrum. Our tag was wrong. It should have been glycine glutamic acid in the middle, not tryptophan. Note that the sequence is running left to right, telling us this is a Y-ion tag, and the terminus we reached was the amino terminus. This is what it should have looked like. I obviously need more practice. That is a rather artificial example, of course, because we have a good match from the database search, so no one would need to call a sequence tag. Alternatively, you can automate the process entirely by using the de novo algorithm. Here's a nice spectrum in another dataset where the Mascot database search has failed to find a match. If we right-click the peak list and choose de novo, we get a reasonably high scoring solution, but with some uncertainty. Right-click the solution and choose Mascot Search from the context menu. Note that we have already toggled the tag type to error tolerant. Distiller populates the query field with the tags taken from the non-ambiguous parts of the de novo solution. We submit the search. And back come the results. Note that the results from this most recent search have replaced the original database search. You can switch back to the previous results by selecting them on the Searches tab. This match looks promising. The sequence runs the opposite way from the de novo solution, but this is to be expected by chance if the de novo fails to reach one or other terminus. If we right-click the match and choose to view the full Mascot report in a browser, we can see from the peptide view that the best match was obtained by placing a modification delta of plus 57 Daltons on the N-term residue. This is almost certainly carbanoidomethylation, which often derivatizes amino groups. This is why the original database search failed to get a match, and illustrates how the error-tolerant tag can get a match when the modification is unsuspected or even unknown, not in the modification list. If you want to get as many identifications as possible, as efficiently as possible, you might come up with a strategy similar to this. A standard Mascot search returns the easy matches. Error-tolerant search returns additional matches, but only for proteins already identified. De novo occasionally returns additional full-length peptide sequences that were not in the database. More often, de novo returns partial, ambiguous peptide sequences. There's no reason to expect additional matches from a tag search, so use an error-tolerant search and e-tag search to find matches to isolated peptides that have a SNP or unsuspected modification. BLAST or MS BLAST if there is a good stretch of clean sequence. Besides the tag and e-tag, Mascot supports a number of other sequence qualifiers. One of these is seq. Note that seq is a filter. It must be correct or there will be no match. The other important one is comp. This would be useful in an ICAT search. Note that comp is a filter. It must be correct or there will be no match. As always, there is more information in the Mascot help pages. These references are a good starting point if you are interested in learning more about the potential of combining mass and sequence information.